Today we are going to solve problem 2.19 of Griffith third edition Introduction to Quantum Mechanics. This problem is designed to the guide a proof of Plancherel's theorem by starting with the theory of ordinary Fourier series on a finite interval and allowing the interval to expand to infinite. Dirichlet theorem says that any function f of x on the interval minus a to plus a can be expanded as Fourier series. F of x is equal to summation over n 0 to infinite an sin n by x over a plus pn cos n by x over a. So that this can be written equivalently as f of x is equal to n summation over n equal to minus infinite to plus infinite cn in pi x over a. What is cn in terms of an and pn? This is part A. We will solve the section A now. As given in the problem, f of x is equal to summation over 0 to infinite an of this sine factor and pn of this cosine factor. Now, what will happen if n equal to 0, sine 0, 0 and cos 0 is 1. So, we can take that as p naught. This is p naught. When n equal to 0, you will get only this term. Sine term will cancel out, so p0. So this is equivalent to c naught because they asked to represent the c in terms of a and b. Then you can change this limit from 0 to 1 because for n equal to 0 you are getting p naught, and 1 to infinite you have this sine term and cosine term. Sine theta can be written as e I theta minus e power minus I theta divided by 2i. That is, I have expanded the sine in terms of exponential. Same thing is for cosine theta. So if you add these two exponential term and divide by 2, you will get cos theta. So now you can group the same term, and you again you get back your n value equal to 0, because we know at n equal to 0 you will get Cn is equal to C naught equal to P naught. That is there. Then you group the similar terms. Here you have e power I n by x by a. Here also e power I n by x a. So here you have an divided by 2i, an divided by 2i. Here you have pn divided by 2. So an divided by 2i plus pn divided by 2 exponential I n phi x over a. Similarly, this negative term. So if you combine these two, e power minus n pi x over a, then you will get here common term is minus an over 2 pi, and here pn plus 2 e power minus I n pi x over a. So we will try to simplify this further. Now we can separate this summation into two parts. That is summation of this positive e power positive I and e power minus I as a separate entity. So now if you separate this, we will get f of x is equal to summation over n 0 to infinite, this positive exponential term, and n equal to 0 to infinite, this negative exponential term. Now here you interchange the limit, that is 0 to infinite to minus infinite to 0. So you make it n as a negative. N is a negative value. So this can be rewritten as minus a sub minus n divided by 2I plus p sub minus n divided by 2 multiplied by. Here also I am replacing n as minus n, so this will become minus of minus n will become plus n. Here this Cn value is equal to this one for positive integer, that is an uh, divided by 2I plus Pn divided by 2. So here I have Cn is equal to An divided by 2I plus Pn divided by 2 if n is greater than 0, that is positive integer. When n is a negative integer, Cn is equal to this one. Here you got Cn. So Cn is equal to minus a sub minus n divided by 2I plus p sub minus n divided by 2. This is when n is, if n is less than 0, and it is equal to p naught when n equal to 0. So naturally this can be written in general. F of x is equal to I am clubbing two summation into single one, that is a summation over minus infinite to plus infinite Cn e power I n pi x over a. But here remember that Cn is a different for different region, that is it is a different for when n is positive integer, it is different for n is a negative integer, and it is p naught when n equal to 0. So we have written Cn in terms of an and pn. So we solved the problem subdivision A. Subdivision P is so by appropriate modification of Fourier tricks that Cn is equal to 1 over 2a integral between minus a to plus a f of x e power minus I nx over a dx. So now we have seen that f of x in terms of Fourier series summation over n equal to minus infinite to plus infinite Cn e power I n pi x over a. Just now we have seen this. So now you take the integral on both sides using this exponential function, that is integral between minus a to plus a e power minus I m pi x over a dx. So here I want to differentiate this n and this one. So here I have taken this as m. So you have to do the same thing on the right hand side also. If you integrate the right hand side also over minus a to plus a e power minus I m pi x over a dx. So here you have plus n, here you have minus m. So if you combine both e power plus in and e power minus im in the left hand side, then you will get e power in minus m pi x over a dx. So you, if you take n equal to m, what will happen? This exponential term will become 1. E power 0 is 1. So this will simply become integral minus a to plus a dx. So if you integrate this, you will get x and apply the limit a to minus a, upper limit a, lower limit minus a, then you will get 2a. So this integral value is 2a. So you have already this Cn. Cn into 2a. You will get Cn into 2a. Why I have removed this summation is this summation is only for when n is equal to m. So n is equal to m, you will get 1, so Ta. So you will get Cn over Ta. Then you bring this 2a to the left hand side. You will get Cn is equal to 1 over 2a integral between minus a to plus a f of x e power minus I n pi x over a tx. So we got this. But here we have assumed n equal to m. What will happen if n is not equal to m? Now we will see what will happen if n is not equal to m. So you carry out this integral in the left hand side. Uh, we have assumed that n is not equal to m. So this exponential term will be some integer multiplied by pi x over a. So if you integrate this, you will get e power I n minus m pi x over a divided by I n minus m pi by a. Now you have to apply the limit. Lower limit is minus a, upper limit is a. If you apply the upper limit, you replace x by a, then a will get cancelled. You will get e power I n minus m pi. Then if you apply the lower limit, x is equal to minus a, this will become negative because a will get cancelled. You will get minus e power minus I n minus m pi divided by this denominator. You know very well that e power I theta minus e power minus I theta is equal to 2I sin theta. Use this relation here. So this will become 2I sin n minus m pi. You will get. But anyway, n is an integer, m also another integer. If you subtract both, you will get another integer. So integer multiplied by pi, sin multiplied by n pi is equal to 0. So this entire thing will be equal to 0. This integral will be 0. You will have this this integral exists only when n is equal to m, for which we have solved Cn is equal to this. Just now we have seen. Then we will move on to the next section. Now, section C is eliminate n and Cn in favor of new variable k equal to n by a, and f of k is equal to square root of 2 over pi a Cn, so that the a and B now become, that is result of obtained in the section A and in section B will become f of x is equal to 1 over square root of 2 pi summation over n, which is equal to minus infinite to plus infinite f of k e power I kx delta k, then and f capital F of k is equal to 1 over square root of 2 pi summation over minus a to plus a f of x e power e power minus I kx dx, where delta k is increments in k from 1 n to next n. So, as per problem, k is equal to n by a. Delta k is, this is incremental from one n value to next n value. That means delta k is equal to pi by a. Then what is f of k? F of k is given as per problem square root of 2 pi a square root of 2 divided by pi a Cn. Naturally, Cn will be, you bring this a to the other side, 1 over a, and this also to the left hand side, that is square root of pi by 2 f of k. Now f of x from section A we have found f of x is equal to summation over minus infinite to plus infinite Cn e power I n pi x over a. Now you can replace all this thing in this expression, because we have to eliminate Cn as well as n. So in order to eliminate Cn, we found that Cn is equal to 1 over a. Here you have Cn. 1 over a square root of pi by 2 f of k. And what is k? N pi by a. Here we have to eliminate n also. N pi by a is nothing but k. So this exponential term can be rewritten as e power i kx, because k is pi by a. So k x, and I am multiplying by square root of pi and dividing by square root of pi. Now the running index is changed from n to k. So this is k equal to minus infinite to plus infinite. Now we got this expression, and we are multiplying and dividing by square root of pi. So square root of pi into this square root of pi will become pi. So this will become pi by a divided by 1 over square root of 2. This pi also will come here. So square root of 2 pi f of x e power I k x. And just now we have seen pi by a is nothing but delta x. You bring it here and it will become delta x. Sorry, delta k. This will become delta k. This is delta k. So I have replaced pi by a by delta k. So this is f of x is equal to 1 over square root of 2 pi summation over minus infinite to plus infinite f of k e power I kx delta k. So we have proved one part of the section C, that is f of x is equal to 1 over square root of 2 pi summation over minus infinite to plus infinite f of k e power I kx delta k. This is one part of section C. Then we have obtained this using our result in section A. Now you take the result in section P. In section P we have seen Cn is equal to 1 over 2a integral between minus a to plus a f of x e power minus I n pi x over a dx. Now Cn is given in this problem is 1 over a square root of pi divided by 2 f of capital F of k, and this you take as it is, except here we are taking k as n pi by a. You replace n by a as k. So this will become e power minus I kx dx. Now you bring all other thing here. Here you can simplify this a, and a will get cancelled when you are. Then you bring this square root of pi by 2 to the other side. Here already there is 2, and this 2, this square root of 2 will get cancelled. This will become just square root of 2. And you bring this square root of pi here. So you will get 1 over square root of 2 pi integral between minus a to plus a f of x e power minus I kx dx. So we solved section C also. Now we will move on to section D. Section T is take the limit a tends to infinite to obtain Plancherel theorem In view of their quite different origin, it is surprising and delightful that two formulas, one for f of k in terms of f of x and other for f of x in terms of f of k, have similar structure in limit a tends to infinite. So, in previous section, we have seen that f of x is equal to 1 over square root of 2 pi summation over minus infinite to plus infinite f of k e power I k x delta k. We know delta k is pi by a. When a tends to infinite, what will happen? This delta k will become smaller and smaller. So infinitesimally small. So naturally this summation will become integral. Also delta x will become delta k will become tk. So this can be written as when a tends to infinite. This can be written as f of x is equal to 1 over square root of 2 pi integral between minus infinite to plus infinite f of capital F of k e power I k x dx. Similarly, in the previous section, section C, we have also seen f of k is equal to 1 over square root of 2 pi integral between the limit minus a to plus a. You remember that it is minus a to plus a. F of x e power I minus I k x dx. What will happen when a tends to infinite? Uh, this delta tx will become smaller and smaller. It will be continuous, and also based on the periodicity, that is if you take sine wave after a wavelength, its structure get repeated, so it will go up to infinite. For a smaller when a is very large, this limit will become minus infinite to plus infinite. So here you can see f of k in terms of f of x, here f of x in terms of f of k. Thank you very much for watching my video and supporting me continuously. Thank you very much.